away.
Thanks, Mosen, and thanks everybody here for giving me the chance to talk to you about one of my passions, which luckily is also something that is pretty actual and current. If you are into the space business, or if you like space overall. So I'm going to ask a question first to everybody. Make sure that you can hear me okay, and that you see my my screen the way it should be. So somebody give me a thumbs up or say yes.
Yes, looks great.
Yes.
Okay, sounds good. Okay, well, okay. So again, thanks for being here today, everybody. I know it's the weekend, and you probably have a lot of good things to do, but you chose to be here today to hear a couple of things about Mars that I hope are new to you, so that you can learn about what we're doing up there. And if you know these things, well, bear with me, and hopefully you can either correct me or ask more questions at the end. I think we have time for that. So what I will do today is show you what we've been doing on Mars for the last 6 months since we landed with the latest mission, Perseverance. And I'm gonna at the end maybe share some of my personal views on what's the future for Mars and for the search for life in space. And but I will preface all of that saying that well, that all of the images and pictures and videos that you'll see today, this is public domain information, so you can go out to the Mars 2020 NASA website, and there's a huge universe of media over there that you can use for for your fun purposes, or even for classes, or for any other application that you want. So it's all public stuff. So feel free to take screen captures, save this, and do whatever you want with it. It's all we all paid for it with our taxes, so we should all be enjoying this today. And the second thing that I wanted to preface the talk today with is that you'll hear some of my personal views on what we're doing and why, and where we're going next. And those views do not necessarily represent the views of NASA or the SETI Institute or my company, Impossible Sensing, for that matter. It's just my personal take on some of the things that we're doing in space. But again, feel free to ask questions or to comment on any of that. I'll be happy to talk about that later. So first off, why Mars, right? And we all know that Mars is one of, if not the closest planet to us. Some of us see it as almost our backyard when it comes to going to space and to explore. And one of the reasons is that effectively Mars is pretty close to us. It's only about 250 million. So I'll say it again, 250 million miles away from Earth, which sounds like a lot, but in space terms, is nothing. Now we can go to Mars in about 6 months if we have a good journey. So it seems pretty close to us, and because it's close to us, we've been able to visit Mars often for the last 3 decades or so with landed assets, right? With rovers and landers, and but our obsession with Mars as a species, of course, predates any of us here today, and we're talking about tens of thousands of years since humans have been looking up in the sky and realizing that the sky is not snapshot and it doesn't look the same ever. There is change. Things come and go. Things look different every single night. And one of those things that was observed very early on was this red hue or red color coming out of this star that was something off and different from any other body or any other celestial object that we could see. And that started a whole field of astronomy with all the ancient civilizations that were looking at planets and stars, and now making distinctions between both. And eventually drove a whole technological revolution actually to build the next telescopes, the next tools to zoom in to see Mars close up so that we can discover the mysteries of this planet, right? And over the millennia that we've been looking at Mars, we have gained an understanding of what this planet is all about. And to the point that not too long ago, last century, about 70 or 80 years ago, a lot of people thought that Mars actually was very much like Earth, maybe a little drier, but it was thought that there were still canals and lakes and oceans on the surface of Mars, and that inhabitants of Mars, and I'm quoting from some of the papers from back in the day, inhabitants of Mars were enjoying nice tropical days, like very much like we do here in summer, depending on where you are, but you get the idea. It was thought that Mars was so close to Earth, it was similar, that they must be Martians, right? Not so much the green aliens that Mosen was talking about earlier, but people like us, pretty much, that were enjoying a whole different planet, also with oceans and lakes and rivers, and that kind of notion stuck for a while, and that's why you start seeing a lot of movies down in the 50s, 60s, 70s about Mars attacks and Mars, and really it was very ingrained into the pop culture that Mars was essentially another Earth, right? And of course, what you're seeing here in this little graphic is this is what we understand Mars was a few billion years ago. So now, today, 2021, and we've been known for a while, maybe a few years, a couple decades, we know that Mars had oceans, or at least lakes, or bodies of liquid water on the surface that was in equilibrium with the atmosphere, so that it was permanent water, liquid there on the surface. And of course, when we think about life as we know it, and life requires water, as a matter of fact, we think that life came from the water on our own planet. So that was very exciting for Mars science, and really discovering that, or being able to confirm that in the past, and again, by the past I mean billions with a B years ago, that Mars had an ocean, suddenly made Mars to be a very, very attractive place to go to look for life 2.0, if you want, right? Another place on the solar system where life may have developed as well. And now we know enough about Mars to know that while it is likely that life may have emerged on Mars, it wouldn't have been life as much as what we see today on Earth. We don't think, we actually can affirm now that Mars had no plants, had no dinosaurs, definitely have no humans, or anything close to us. But we, or a lot of us in the community, believe that based on the evidence that we have, there is a good chance that that microbes, even bacteria, may have emerged on Mars, if not at the same time as on Earth, perhaps earlier than on Earth, or after, but within the same time scales. So that's what's bringing us today, and to this wave of missions that you've seen in this century, starting with Spirit and Opportunity in 2004. And I know a lot of the kids listening today weren't even born then, probably, but we've been sending very, very sophisticated laboratories to Mars for almost 20 years now. And in 2011, we launched Curiosity, which is a rover that has been driving on Mars for 10 years now. And now the younger sister of Curiosity, Perseverance, landed early this year, and it's been driving and doing amazing science on Mars for about 6 months. But all of this is part of the program that NASA, in collaboration with other agencies across the world, has about really finding or trying to find life on Mars as a potential place where again, life might have emerged in the past. And of course, and I will touch on this at the end, Mars sounds like a perfect outpost, right, for a future colony of humans, based on what it is, the resources that are there, and the role it's played in our history about as a beacon, or as a place that is pulling us to explore because it's there and it's so close to us. So that's Mars in a nutshell. And this is the plan that again, NASA, but also, of course, working together with partner agencies around the world, has developed to blend in a very creative way, in my opinion, science, exploration, and technology, plus our human curiosity to go to where we have never been before, right? To explore the unknown, the final frontier. And now that's crystallizing in a very complex yet feasible, given appropriate funding, of course, but technologically feasible way to eventually move on from sending robots only to eventually land humans on Mars. Some people think that as early as the 30s, the next decade. Some of us are a bit more cautious about that, but it's going to happen certainly. It's a matter of when, it's not a matter of if. And so the mission I'm talking about today, Perseverance, Mars 2020 mission, is part of this big picture, big plan that is now, for the first time, targeting the question of, is there life on Mars? And we'll see how this mission is going to tackle this question in a few minutes. But before that, for the non-initiated, for the newbies on Mars, I just wanted to put in a couple of Mars facts here, so that we all get into the same page and start to understand, why don't we go to Mars every day? Why is it so difficult to get there, right? So to start with, here is a comparative of how big Mars is compared to Earth. So the size diameter of Mars is about half of Earth. So it's substantially smaller, which has certain effects, as you will see in the next few slides. But it's not small as the Moon, and it's definitely within the right size for us to actually, and very, very scientifically now, determine that Mars in the past had a core, liquid core, nucleus, very much like the one we have on Earth, that back in the day had a magnetic field, right? Exactly like the one we have today, that protected Mars from the harsh cosmic radiation and solar radiation as well. And that's why back in the day, when this magnetic field was present, Mars was able to sustain liquid ocean and liquid rivers and lakes on the surface with an atmosphere. All of that is gone today, and all of that is making Mars even more difficult to explore, of course. So, of course, because it's smaller, right? It's going to be lighter, and turns out that the composition of Mars is pretty much the same as Earth with neighbor planets. So you can make a very quick conversion of, if you know the density of rock, which we know, of course, and we know that the mass, how heavy mass Mars is about a 10% of what the mass of Earth is. And that's important, of course, because that drives gravity, right? As you know from physics class, the heavier or the bigger the planet, the bigger the pull towards you. So the bigger your weight apparently will be in a scale. So if you were to weigh 100 pounds on Earth, and if you feel like you're heavy and you go on a diet, take it easy, go to Mars, and suddenly your number is going to be about 40 pounds, so a little skinnier than you will be here. But again, it's because, of course, Mars is much smaller, and obviously another fun effect of that will be on humans and will be on humans is that you can jump higher, right, and you can jump faster and longer if your suit allows you to. Again, because the gravity is about 60% of what we're used to here on Earth. So it will be a breeze basically to play basketball, right? And slam dunk, no problem. The problem comes with temperature, right? So you guys are used to pretty hot and pretty dry, but mild overall climate over where you are in California. I live in St. Louis, Missouri, which is a little bit more extreme, with especially the winter, but we have it pretty easy on Earth here, and the average temperature on the planet is about 57 Fahrenheit, so pretty manageable. But if you go to Mars, you're gonna have temperature swings that are pretty brutal. So on a hot day on the equator in summer on Mars, you may go up to 130 plus Fahrenheit. Think about Death Valley over there, California, even worse than that. And but the hard part comes from when the sun goes away and the night comes in, because think about desert. So Mars is the extreme desert where cools down pretty quickly because there's no atmosphere. So you can go down to minus 130 Fahrenheit as well. So you look at the range of temperatures on Earth is something like this. On Mars is something like that. So to explore that and to build computers and robots that work in those extremes, that is a pretty tough job to do. Just to give you an example, if you've been outside in the summer with your cell phone outside in the sun, most of you, like me, have gotten the message: phone is overheating. Take it down to the shadow, right? And you're talking about an 85, 90 degree day. So think about cranking it up even higher. But worst of all, cooling it down to way below freezing here. So it's hard to make technology that actually works in that range. That's why we don't go to Mars very often. We just need to keep building the best tools to be able to sustain life there, right, and to operate over there. And I'm not even thinking about humans there. That's going to be a whole challenge to keep people alive and well there, on top of growing their own food, perhaps on greenhouses. But that's technology for the young kids today. We can only think about this now and let you guys tackle that when you're in school and working for this, hopefully in future. So, and the last fact here, like you probably know, obviously Mars is farther away from the sun, so it takes longer for Mars to complete 1 year, so to go around the sun one time. Exactly, it's about 2 times as long as Earth, right? So for every Mars years, for every 1 Mars year, the Earth goes through 2 years, and you'll see why this is important in a few minutes. But all of that considered, is the reason why we're still about 50% success rates when it comes to landing on Mars, right? So it is very difficult. Mars is hard, like this score says here. I think this is a bit outdated, and I think now we're probably about 20 wins from Earth and 24 from Mars. So we're about 500 win-loss record. But I just wanted to kind of convey the message that it's not trivial. It's not easy to build a team that can put together a mission that can successfully land on Mars and successfully execute the science goals that we wanted to do. So something that inspires lots of us. We do it because it's hard. We do it because there is certain satisfaction into tackling a challenge of this magnitude. So yeah, it's still hard, and it's 2021. So we'll get better, but it's still going to be difficult, and it's nothing. It's not a done deal. It's not a piece of cake yet to do science on Mars. Part of the challenges, and back to the different orbits of Mars and Earth, is that to make sure your trip is the shortest, to make sure that it only takes you 6 months to go to Mars and not 12 months, what you want to do is you want to time very perfectly the time when you launch your mission with the position of Mars in the sky. Because what you want it to happen is that you travel the least amount of miles, because A, it's cheaper, so you have to use less rocket fuel, and also it takes shorter time, so your instruments can don't have to suffer a long journey in the cold of space before getting to destination. So very much like you do when you plot your route in Google Maps. I want to go there, tell me the shortest route. We do the same with Mars, and this means that we only have an optimal window to launch to Mars every 2 years. So we set the cadence for Mars launches pretty much every other year. So if you miss your window, most likely you're going to wait till 2 years from now to do that. So this video here is an animation of what we thought would happen with the current mission. So this video was, of course, made in preparation for the landing in February this year. And we know pretty much what happens on Mars. So what happens is that there is an atmosphere. It's pretty thin, but it's still there. So, if you were looking at the sky from Mars on a landing day, you will see something like this. And what it is we're using the atmosphere to break down. We have a shield that will slow down, and this is called aero braking. So we'll slow down the spacecraft by using the atmosphere and slowly correct course until we slow down from about 100,000 miles per hour to about 10,000. Then we deploy a parachute, very much like the one you see here, and slowly keep braking, slowing down the descent, while now we're looking at, okay, where do we want to land here, right? What is the good place to touch down with this rover? So eventually, eject the covers. Now we're safe. We find a place, and then we drop yet another spacecraft here. This is the core of the mission, which now has rockets to further slow down. Now we're slowing down from about 1,000 miles per hour. Now we're slowing down to 0, right, in about 2 minutes. So this is a pretty low power that we use there to really locate, pinpoint the landing site that we like, something that is safe. You don't want to land on a rock, right? So you want to land in a safe, flat place, and then, but you want to land safely, very smoothly. So once you stabilize the spacecraft, we winch down, literally with a pulley, the rover, and lift off, go somewhere else, crash far away from the action, and now we're on Mars, right? So this is what we were all hoping for. What happened in February this year, and luckily, of course, everything went according to the plan. But I don't get tired of showing this video here. And if you were watching the landing, or you learned about the landing, I always ask people to try to remember what you were doing back then, because at least for me and a lot of my colleagues that have been working on this mission for 10 years plus, it was a very special day, of course, because your work now is on Mars and it's ready to work. So it came a lot of emotions every time I see this video. But it's short, but it shows you exactly what humans working on the mission were seeing the day of the landing. Hopefully the audio works. Yeah.
Propulsion, go. EDL safety, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed, and we're seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Tracking maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars. And taking the bend of top flight.
Yeah, so I don't know if you're a bit like me. I mean, I'm still feel like pretty emotional every time I see this video. And when you see a veteran senior space rocket scientist, crying, right, when you land on Mars, that tells you that this is really accomplishment, right, for the whole team of people here. So again, it's still difficult and it's still hard to get there. So everybody's very happy when we do it. So all right, so what do we have on Mars right now with this mission, right? So so there is a collection of different instruments, and each one of them is doing different things. And I'm not gonna go through the gory details of what everything is doing here, but just to give you a breakdown of how we're doing things there. So there is a lot of cameras. There are about 28 cameras on this rover that are helping the team decide what rocks or what targets look very interesting. And based on that, we drive close to the target and we deploy the instruments that you see in the arm here on the front of the rover. And those are very sensitive cameras that are using lasers and X-rays and other type of radiation to interrogate the rocks and tell us about the elements and the chemicals that are on those rocks. Once we're happy with what we see there, if we're happy, then we do what we've never done before on Mars. This is a first for this mission, which is to collect a small core. A core is a tube of rock that you extract from the rock. In this case, we're coring down to 3 inches into the ground, about half an inch diameter. So it's a tube that contains a sample from the subsurface, which is something that we've never done before on Mars. We have excavated with arms. We have a drill on Curiosity that gets powder out, but we have never before till this mission get an intact piece of subsurface terrain from Mars. This is one of the first innovations of this mission. And the importance of this is that by keeping the texture and the geometry of this rock, when we analyze it, then we learn about not only what the chemicals are, the compounds, but also how they distribute, how they sit compared to each other, tell you the whole picture of what's under the surface of Mars. But of course, we will not do that on Mars because the technology that it takes to scan the samples for looking for microbes, we don't have that ready for Mars yet. So what we're doing with this mission is we will collect between 26 and 34 of these tubes, these cores. We'll seal them hermetically and we'll leave them behind in a safe place somewhere on Mars on the surface. And we'll wait for a future mission to go there, pick them up, and bring them back to Earth. And on Earth, of course, we'll have the best labs in the world to analyze them and to really interrogate the samples to look for that life that may or may not be there. We don't know, so we'll have to wait, unfortunately. So that'll be another 12 years of perhaps of time to wait till these samples come back to Earth. So if you're a young kid now and you want to be the one who finds life on Mars, yeah, keep studying science and chemistry, and maybe you'll be the one who gets to touch the sample and to find the microbes there, hopefully. So that's in a nutshell what the mission is doing these days. And this is a little animation that explains with video much better than what I did with my speech what we're doing on Mars. So I'll walk you through this a little bit so you can actually visualize what we're doing on Mars every single day, basically. We have a team of people working day and night on doing exactly what you're seeing here. So we have a mast here that you see, the white box on the top that has a telescope that can shoot a laser and tell us about what's under. And again, once we see what we like, then we deploy the coring tool, which is this machine that you see here now, that is gonna drill and get this core the way that I was explaining to you earlier. So it's an intact core, right? So it preserves the texture and the geometry of the sample. So the instrument, then the arm will push the core into the rover, and that's a whole different mechanism now that is gonna do two things, many things, but it's gonna pass this tube around to one stage that is designed to verify that we actually have a core, right? Because this is all done automatically. There's nobody joystick in this machine. You send a command and you go to bed, and in the morning you hope that it's been done. So this is all done automatically on Mars, and this machine is going to measure the volume. It's going to verify that everything is there, and if everything checks, then it's going to seal the sample, much like when you seal a can out of your preserves. So similar thing, of course, different materials, but and high tech, but the same deal. And then it's going to store it in one of these bays there, and yeah, repeat this 25 or 26 times at least over the next 2 years. So right now we've collected 2 of this, and I'll show you what it looks like in a bit. and we just keep moving, right? So this is what we're doing. We know where we're going. We have a target, and now along the way, we find hotspots or places of interest where we're actually doing the science and getting those scores that you saw there. So now show you a few of the pictures that, again, you can go online and find these things there, but I picked them because they're especially inspiring to me. And like, for example, this one is a panorama of the landing site. This was taken the first week after we landed. And this is where we landed. This is home, at least for a while we checked everything on the rover. So we spent some time there, and we start showing interesting things like that little rock that you see there. That's about 30 to 50 meters. I don't remember the number. Maybe 100 feet far away. But now we have a zoom camera that we can actually zoom in and see these amazing features here. And what you see here is a rock that has been shaped by millions of years of dust abrading the rock and shaping it into a nice sculpture, actually. So this is what Mars is all about, this wind loaded with a little bit of silica and particles of sand that is very slowly abrading and exfoliating textures and creating shapes like the ones you see here. So pretty spectacular. This is another panorama taken of the landing site, and we landed on a delta valley. So we picked this place because it's an impact crater, so it's lower than the surrounding. Hence, you see the mountains here. We're in the valley, and because the impact of the meteorite created this step in terrain, there was water that flowed through a canal, through a river, very much like you see here, into this valley where we are now. There was water flowing here billions of years ago, and we like deltas of rivers on Earth because they concentrate sediment and a lot of rich organic material that we use to grow plants. Very great place for farming. So we're thinking that all these similar sedimentary rocks that we have from Mars, shaped by water, they may contain sediments that have traces of organics, of life, perhaps from the past. So that's why we picked this landing site here. So we're going to slowly drive up the hill over the next few years on Mars. So this was the very first drive of the rover. So to show that it worked, we got a selfie of the tracks of the wheels here. So show that all the wheels work, everything's good, and we're ready to keep moving. So over the 6 months post landing, so the last 6 months, we have been taking pictures, readings with science, environmental data about wind, solar radiation. But only about 2 weeks ago, I think it was September 10 or 11, when we collected the very first core. So remember the tool that it was drilling down and getting this tube out? So this is what the camera that is looking down into that core showed us. And this was a milestone in the mission because for the first time now, again, we have in possession, like we own now, a piece of the subsurface of Mars, 3 inches down, that is intact. It contains everything the way it's been deposited there for billions of years. So it's a very precious sample that we sealed immediately after verifying, and now it's ready to come back to Earth as soon as we can get it back with a different mission. This is a different view of the rock, and this is the tool that we use to verify that we actually have the core. So it zooms in at different steps, much like you do with your photo camera, right? When you dial in and zoom into your object. So here we verify that we have the sample in the same way. And here is the 2 holes that we got in this rock. So we picked 2 just to verify if there is any, basically to have one blank that we use, or one test if you want, that we play with it. We took pictures and we let it open in the air for a while just to verify. So it may be contaminated by the atmosphere. It may be oxidized or transformed. And the second one, we took a sister hole here. We took, in this one, we sealed immediately, now that we know that the tool works as expected. So these are the 2 first cores, the first samples that will come from Mars to Earth in history. So very important moment for science. And another picture, just personal interest on these panoramas that I think are something spectacular. And if you have been in Death Valley or other deserts, this does not look very different than Earth in some ways. You have red textures because there's a lot of iron that is oxidized, and you have different shapes and rocks that resemble some of the places that you see on Earth. So to me, this is a strikingly beautiful picture because if I don't know that this is Mars, I wouldn't be able to. I wouldn't bet my house on it to put it in a way. So and same here. So you have formations like this that are shaped by both water. That's what you see, the little layers that you see on the top of this mesa. All those layers are different periods of time where water was sedimenting, was depositing material into the bottom, layer after layer, year after year, for millions of years. And eventually the wind comes in and shapes it out in a way that looks very much like the Southwest in the US, some places if you've been there, but it's of course Mars. I promise this is Mars data for real. So one of the first things that another first of this mission is that we have microphones now. We have 2 microphones that are taking stereo sounds of Mars. So I'm going to play you a couple of things that we have seen there. So this is the wind of Mars. So sounds kind of something like you've heard before, and it is so because it is exactly what you think wind. And I hope you can hear my audio. If not, somebody complains. But here what you hear is different winds that are carrying a little bit of dust, and that's what makes the noise here into our microphones. Second audio that I'm going to play is a tool, the one that is in this mast with the telescope that you saw in the white box on the top. That has a laser that zaps rocks, literally. It shoots rocks, and it's so powerful that it makes plasma. It makes a little ball of fire every time it hits the rock. So this is what it sounds like. Every single click, click, click is a shot of laser on the rock. Are about 20 feet away. So we're zapping rocks on Mars as we go, and now we can listen to it as well. This is what the wheels or what the rover sounds like when it's driving around Mars. So it sounds pretty ghostly or spooky if you want, because you have metal wheels that are crushing against rocks, right? So it's very loud and very metallic or very robotic if you want, like almost on the movies. But it's it's exactly what it sounds like. And there's a hum here on the background, and that's the motors on the wheels that are constantly spinning to give us the motion that we need. Yeah, and if I can stop it, is it still playing? Yeah, I think it's still playing. Yeah, now all of them are playing now. Let's see. Now what you're hearing here is the helicopter flying. So I'll go into this before. I didn't want to create too much emotion about this yet, but we also have a helicopter this time, and it's a drone basically, and it's flying on Mars as we speak. So this is what the spinning blades sound like on Mars. Yeah, so you'll see a couple of videos of this coming up. So we're over excited because it's the first time we actually have ears on Mars on top of ice. So we're getting much better at knowing what Mars is like. So this is what the helicopter looks like. So I'm going to play this video, which shows mostly Earth captions, because wanted to show you what it takes to actually get this to work on Mars. I know some of you will become engineers and scientists, and the technology that went into making this happen is absolutely fascinating. So there's a video of how some of the testing went on Earth. Yeah. So it took many, many years to come up with the design of two blades that spin opposite. And of course, the problem is, how do you transport that to Mars, right? So somebody very smart figured a way to stow the helicopter under the belly of the rover, and a system to deploy it on Mars in a safe way. So this is what happens. Slowly, one leg comes out, and then when everything looks good, the system moves the helicopter into horizontal. There's a little hole on the deck here to accommodate this leg. And then when everything looks good, then 4 legs are deployed. And eventually the helicopter is now ready to be dropped on Mars. So of course, this in the lab worked pretty well, but we didn't know if it would work on Mars. It did, news, but it was another exciting moment of this mission, is to show that actually we can bring a helicopter and safely drop it and make it work. So all this was animations, wishful thinking, and all this came true, thankfully. So now we have a helicopter flying on Mars and taking data for us. Yeah. And I think here this is a real picture now. Actually, it's a video of a helicopter on Mars. This is from about 3 months ago, I believe. So you see it spinning on its axis. This was the first flight or second flight. And we're trying to see if it actually does the things that it's supposed to do, right? Go up, go down, spin around before we send it on a mission far away to scout for us. So this was the very first proof that, yeah, we're flying on Mars. So milestone again for humankind is we are flying with power. So we have a controlled aircraft power flying on a different planet. Another first for NASA and for us. So, and this is a collection of images in a sequence on a video, if you want, of the shadow of the helicopter as it's flying on Mars. So this is looking down from a flight path. This is the shadow that is projecting on the surface. So the idea of this helicopter is not to do amazing science. You see the photos here. It's a very low resolution. The camera that we're flying here is much worse than the camera on your cell phone. All the effort went into making sure that we could fly on the very thin air on Mars, and so we couldn't spare any single ounce of mass to fly anything big. So we just put in a camera just to get a few pictures to demonstrate that actually we can do science, or at least get pictures from the air on Mars. So another success here. So if you're curious to know where we are every day, so all you have to do is to Google or use your search engine of preference, where is Perseverance? And NASA built this very nice tool that allows you to know where we are. So we landed here on the top of the screen, and the white path is the drive that we've done with the rover, 1.5 miles, a little bit more, over almost 2 miles now. And the yellow path is the flights of the helicopter. So helicopter flies not too far from the rover because it needs to send signals, right? All is wireless, so the closer the better. So we're kind of doing a dual air vehicle mission combined in tandem. So you can check this in real time, basically, and overlay different layers of information and stuff like that. So very nice tool if you're curious about this. And just to end this and give you guys time for questions and comments, this is what's happening today, right? And if everything goes well, we'll have this mission working until March or April of 23, so another year and a half. If everything goes to plan too, and the rover is healthy and safe, we will seek additional funding from NASA to keep operating the mission for 2, 4, 6, 8 more years. Very much like we're doing now with Curiosity. So year number 10 and counting. We're hoping that this mission can go for a few more years to keep us showing amazing stuff on Mars. But what's happening after that? So this will be the red mission. This is on red is what we have today. The cache is this little depot or box that you saw earlier that contains all the tubes, all the cylinders, and that will be dropped somewhere on Mars. And in future, NASA and the European Space Agency will launch another mission that will land on Mars nearby. It will deploy a small rover, very simple rover, whose job is just to find this cache, pick it up, and take it back to the lander, so that it can be sent back to space from the Mars surface. So we've never done this before. We never launched anything from Mars. We have a good idea on how to do it, but again, it's still a little risky. That's why we chose to do it in the next mission, not this one. This one is focused on getting sample. Next one is to find and get the sample back. And eventually, a third mission will fetch the samples when they're in orbit on Mars after they've been launched, and they will bring them back to Earth. And so the plan is to launch this within this decade. So if we're lucky, we'll have the samples back here by 2030 at the latest. Of course, things can go wrong and things may be delayed a little bit, but the plan is there, and there is a will by different agencies to actually do this. So it'll happen. So be ready for that. Just 10 more years of wait. So this is just a fun graphic of what we think launching from Mars could be, like a rocket, like a gun, basically, into Mars sky from Mars with the samples. So we're all hoping that this becomes reality pretty soon again. And of course, this is where it becomes even more futuristic, right? And what are we going from there? What is next for Mars? And we can keep sending robots forever, and that's fine. But there is still certain itch, right? There's certain human quality, certain human need to explore, to go to the next frontier, just because it's there, right? Arguably, there is scientific benefits to sending humans to Mars. After all, we are a species that we have genetically imprinted on us to explore, to expand, to colonize, and there is no question that we will become an interplanetary species in time. And Mars, we see Mars as our first outpost in a different planet, a place where humans can learn how to work in much more extreme environments than what we have on Earth. Forget about Antarctica. Antarctica is a piece of cake compared to Mars, but a place also where we can start to think about psychology, about politics, even, right? Because it's a whole different way to operate there when you're far away from Earth. And every single breath or step could be your last, because it's hard to be there. So suddenly the way you think about life and priorities is going to be very different. So we don't even know how this is going to look like, but for the young kids today listening to this, I mean, this could be you in about 20-30 years. So not too far ahead. And but of course, I don't want to end the talk today without mentioning the moon, because inevitably anything we do in space, definitely Mars, goes through the moon. There is no humans on Mars before having humans back on the moon. There is no missions to Mars without launching them from the moon in future. There's certain benefits to that, and that's a whole different talk, and we don't have time today for that. But I wanted you to know that if you didn't know already, that NASA has a very ambitious program called Artemis, and Artemis is aiming at landing the very first woman and the next man on the moon in the next 2 to 3 years. So we haven't been there since the 70s, not for the reason that there wasn't any advantage to having humans back there again. We have enough samples and we know enough about the moon for now. that we need to keep thinking about it before we go back. But now we know what we're looking for on the moon. Now we're looking for resources like water that we can use for rockets. Now we can split water into hydrogen and oxygen that we can use to breathe oxygen and to burn cleanly for rocket fuel to launch missions from the moon. So that's the moon is the gateway to space for us, and it will become a destination for pretty much every single mission that goes to space. It will stop by the moon, refuel, even mission will be built on the moon, and we launch from there. And that's the step, is moon to Mars, and that's what we're all working on right now, not only at NASA, but also across other agencies. So I will stop here, and if we have time, I'll take questions, comments, concerns, anything you guys want to talk about.
Great, Dr. Sobron. Yes, you do have some questions in the Q&A box. So the first one is, will you track the cache by coordinates or will it be by a GPS? You mentioned the extreme temperatures. Are they currently impacting the mission in any way?
Oh, what a great question about the GPS. So there is no GPS on Mars, all right? So GPS works by having satellites orbiting the planet and tracking the difference it takes for signals to travel from your location to different satellites. So we only have 2 or 3 on Mars, and they're not ready to do this kind of tracking. So we don't have a GPS, we don't have a map with an X, right, where we're gonna land to find this cache. So the way we're gonna do this, we're gonna take a very high resolution orbital imaging of the landing of the place from the cache. So we'll find certain milestones, certain features, rocks, or other things there that will be telltale for an orbiter to look down, take a picture, and even if we can see the cache, because it's going to be very small, and from orbit we cannot see it perhaps, but we'll be able to see a mound or a big rock or a feature. Maybe we drive in circles and we make a little channel around, right, to mark the place. But it's the only way we're going to be able to find it is by looking at pictures from orbit. And as of the second part of the question, the temperature, yeah, absolutely. We do not work by night on Mars because all the energy that we utilize on Mars by night goes to keep the electronics just warm enough that it doesn't freeze. So it costs so much energy to keep things surviving, to warm them up enough that we cannot operate by night. So the effect is that any science, any operations happen by Mars daylight. Yeah.
And can the cache be moved by the wind so you can't find it?
No, the wind. Well, it's a good question, but you have to remember that the atmosphere on Mars is very thin. It's about 10% of the atmosphere on Earth. So even if you had 100 miles per hour wind on Mars, it will only be like about 10 miles per hour wind on Earth because you're not moving too much air. The wind doesn't push anything because it doesn't have any mass to move things around. So it couldn't tip or move around any big item like this cache. What it will do, most likely, it will bury it a little bit. It will deposit sand on it, perhaps a layer that it will cover it with a blanket of sand over time. But we're hoping that we'll catch it before it gets covered in dust forever.
Great. And then I have a question from Alice. Why must samples be taken back from a separate trip?
So there's many reasons for that. The 2 most important ones is that to bring samples back, we need to launch a rocket from Mars back to Earth. And like I said before, we have never done that before. So NASA, with good criterion, in my opinion, doesn't take too many risks when it comes to missions of this type. The cost of this mission was about $2 billion plus, so pretty costly, and already risky enough that it is not worth adding an extra risk on the mission, something that can go wrong on top of the things that will go wrong in this mission. So it was decided that it wasn't worth the risk. And that's one of the reasons. But at the end, came down to practical questions, and is this mission will have to land a rocket full of fuel to shoot back into atmosphere. So you will we will have to double or triple the mass that we had to land with this mission already, which was borderline impossible, but we still pull it off. So it will have been impossible to use this architecture of aero braking with the shell, parachute, and then the crane with an extra added weight like it would be for this rocket. So the choice is to send the science mission now, which is the one we have today. And the follow-up mission, the fetch mission, it's only doing fetching. So no science, so no spending any effort and mass and technology into science. It's just to go find and launch back. So every ounce of mass will be into rocket fuel for the next mission.
Great, thank you. And Marian asks, some of the exposed rocks sitting on the Mars surface in the photos look very jagged and fractured, as opposed to the smooth wind-shaped rock in one picture. What process created and left them there, e.g. product of ice fracturing, meteorite impact, etc.?
Yeah, that's a fantastic question. So there's multiple reasons for things to look different. And the most important one is that the rocks are made of different stuff, right? So, the rocks that you see, they are very round, look very smooth boulders. Those are typically sedimentary rocks that are made of clay or silicates, even carbonates. So they're very soft, comparatively speaking, and those can be shaped by either water or wind, for that matter, and sand into these very, very nice round boulders and smooth surfaces. The rocks that are more angled and rough and fractured, like you say, those are igneous rocks. So they're not sedimentary. These are volcanic rocks. They're lava, basically, like the one you see in Hawaii today. Those are basalts and rock that it's much harder. And when water and wind process the basalts, what they do is they carve out, they bleach, basically, and leach out metals and elements, and they leave channels of holes, little voids, little tunnels, if you want, and that's why the things look different, depending on what you look at and what you're looking for.
Thank you. And Mandeep asks, is it true that we have to go back to the moon first, or do we have any current rocket? And do we have any current rocket that could get us back to the moon?
So, we do not have to go to the moon, but it makes no sense not to go back to the moon and start launching from the moon. But I understood the question in two different ways. So I'm going to answer in two different ways. So when it comes to future missions to Mars and elsewhere, Jupiter and the moons of Jupiter, Europa, Saturn, Titan, and Enceladus, all the places where we think life may exist as well, and they have oceans today. To go there, we have rockets that we can launch from Earth. It will take 5-6 years, and it takes so much because it's far away, A, and B, because all we can do is to fill up a big rocket full of fuel, launch it out, and let it go. So if we were to launch from the moon, the cost of doing this will be about 50 times cheaper because there's no gravity on the moon, or there's much less gravity on the moon. A sixth actually of the gravity, so it's much cheaper and easier to launch from the moon. Also from the moon, you can get hydrogen from the rock on the moon, from the surface, and you can use that for fuel. And that fuel burns cleanly and releases a lot of energy that can get you to where you're gonna go faster than what we do today with normal chemicals on Earth. So that's when it comes to using the moon as a gateway. When it comes about the moon, because the moon, well, so again, as we develop capabilities as a species to live off planet, eventually the Earth will cease to exist, either by our own doing as humans, or just because the sun will go supernova in a few billion years and the Earth will be gone. So if we are to persist or persevere as a species in the universe, we need to learn how to colonize other planets, to settle elsewhere. So the moon is a few days trip. It's right here. We know how to land, and turns out that beyond being a good place to practice, there is other benefits of the moon, which again I said it can be used for building or for getting rocket fuel. but also you get resources that humans can use to construct rockets. So there is all kinds of metals and rare earths on the moon that we can either use on the moon to build our habitats and rockets, but also we can maybe import back into Earth to use to build, all these new technologies that we're using now to decarbonize. And I'm talking about the wind turbines. They use rare earths for the magnets to generate electricity as things are spinning. Solar cells, they use beyond silicon, they use rare earths to optimize the transformation of solar energy into power, right? And of course, batteries, the ones that Tesla and other cars need today, those require rare earths, of which we don't have too many on Earth. So the moon is rich in those rare earths. So there is a moon economy that is shaping up now that will make us eventually mine resources on the moon, both for in situ use on the moon, but also perhaps for import on Earth for our own purposes here on this planet. So in that sense, and this is personal opinion, I think it is imperative that we start going to the moon, pretty much like constantly, which we will. And think about the first aviation, right? The first pioneers of flying on Earth. Flights were few and there were not many people doing that because it was risky and costly. But eventually, flight becomes a commodity. It's basically free, essentially, to fly now. If you forget about COVID, but before that, it's very, very, very cost-effective now to fly on Earth. The same is going to happen on the moon. There'll be shuttles, and in our lifetime, we'll be able to go to the moon for a weekend, most likely, to spend time there just to relax. Well, if living in a habitat in a suit at minus 100 degrees or plus is relaxing, then that's what the moon will be for tourism. But yeah, so that's going to happen, and it's inevitable. Yeah.
Wow. And how many hours a day can the Perseverance drive? Can you talk a little more about its nuclear battery?
Yeah, so the power supply is nuclear, or as we call it, radioisotope thermal generator, so RTG. So we chose that versus solar panels on Mars because the size of the vehicle is so massive that the panels that we'll have to fly to support all the services, all the power we need and thermal control, it will make the panels too massive to be practical. So just couldn't do it. So we went the nuclear or the radioisotope way. But also because by using RTG, we can operate by night. And I know I said before that we are not doing science by night, but we are keeping everything in good shape by night, and that requires massive amount of power. So the only solution for that was to use the radioisotopes. Now the other benefit of that is that we don't. There is clouds on Mars, right? So there is. If you look at some of the pictures from the last month, we see clouds. The clouds are dust that is coming, and there is cyclical dust storms on Mars. That was one of the reasons why Opportunity actually died, is because it got caught in a 2 or 3 month dust storm that blocked the sun to a level that the solar panels couldn't generate enough power, and it just froze to death, basically. So by using RTG, we don't depend on the sun for that, so we can survive longer. And that's why these missions will last longer than Opportunity and Spirit if everything goes right. Also allows us to drive faster because we have more juice, right? So we don't drive very far. We drive about 100 meters a day. That's about 300 feet a day. And part of the reason we could go faster, but the problem is that there is nobody joystick in this. There is no radio control, right? No PlayStation remote. The system, the rover has to navigate safely, identify obstacles, paths to go, and on its own. And that is still an emerging field of machine vision to support safe driving. So we are very conservative. as to how much autonomy we want to give the rover, because again, if it breaks one wheel, then the mission is probably toast. At least there's no more driving around, which is bad. So, more often than not, the rover stops when it thinks that it's too hard, and it stops there for the night or for the day until the next link of data, and it tells home, hey, NASA, it was too hard, I stopped, tell me what to do next. And then the engineers, the drivers of the rover, they'll plot a path for the next sol, the next day, and the rover will do that, and so on and so forth. That's how we drive from Mars. So it's pretty slow because of safety. Yeah.
Awesome. And what would it take to set up a network of GPS satellites at Mars?
So about $500 million per satellite multiplied by 24. So $20 billion. So that is about the budget of NASA every year is $20 billion. So for the whole agency, which is doing, for which Mars is about, I'm gonna say, don't take my word for this, but it's gonna be about 5% maybe of the NASA budget goes to Mars. So it would eat up NASA's budget for the next decade, basically only doing that. So it's not gonna happen. So what's gonna happen is that more countries now, and you probably heard about the United Arab Emirates and India. They became Mars powers in that they successfully launched missions this year. Very simple missions. They're low cost to the standards of NASA and ESA, but they proven that for low cost, $100 million, that range, you can launch a Mars satellite and have it orbiting Mars, getting pictures and getting data relayed back and forth. So what we think is that this decade, in the next decade, so in the next 20 years, more countries will adapt to the collection of Mars, the Mars Club, and there will be a network of about 10 to 15 satellites that, if we do the job right and work together, they can be networked in a way that enables a GPS type solution for Mars. But that's still pretty futuristic, I think, utopian in a way also. So don't take my word for that. I think that's what we all hope, but it's hard to predict at this point.
Really cool. And our last question is from our own professor of astronomy at College of San Mateo, Alicia Polomsky, who asks, does Mars have enough magnetic field anywhere on the surface to use a compass to determine north?
No, the answer is no, unfortunately. So the just to give some context here to the answer, we know there was magnetic field on Mars back a few billion years ago. So Mars has or had a liquid core that was rotating very much like our own core on Earth. And if you know your electromagnetism from school still, when you have a liquid metal or a metal that is moving around fast, or you have a lot of it, it creates a magnetic field around it. So that's what we use on Earth to navigate with compass. For those of us who still use a compass once in a while, and not your cell phone, but we don't have such a thing on Mars, unfortunately. So we're going back to the nautical era on Mars. I'm not kidding. Like, we're using the star charts on Mars to navigate and to plot courses. It's called, I think it's called star nav. There's a name for that, but yeah, we use the stars. Yeah.
That's awesome. Thank you so much. And even though we don't have any more questions in our Q&A, Mohsen, did you have any questions for our presenter? I have a feeling you do.
A couple of things. First of all, I want to thank you so much for the super informative discussions. I don't have a question, but my wife, who is sitting next to me and listening, asked me a question to ask you. And the question was that, why can't they make the cores a little bit longer, and should it be always drilled into the rocks?
Wow, what a good question. So, yeah, of course we could make the core a little longer, but the problem is, well, where do I start? So it took about 10 years to figure out the mechanism that could extract a little bit of core from Mars, given what we know about the texture of the rock, density, composition. So we thought that if we were to do it deeper, say a foot, right, a core, like you do in industry mostly, or environmental sciences, the risk that most of it will be broken, or the drill bit will get stuck on the surface. Because remember, we're talking about minus 80 degrees Fahrenheit, maybe. So when you're coring and you're basically melting some of the ice, if there's some ice there, but it will cool down quickly, so you get stuck very quickly. So the 2-inch metric was a compromise between, let's get deep enough that we're far from the atmosphere, so we're older and safer from the radiation, but not too deep that we can get stuck. So that was the compromise of that. And the need to drive to the rocks, for now, we have to do it. We cannot fly to the rocks and drill the rocks yet. We have built things. Actually, my team has built tools for doing that. But the problem, again, on Mars is that the atmosphere is very thin. And to fly, you need lift, right? So the thicker the atmosphere, the better, because you can spin thing and just lift off easily. On Mars, that's not the case. So we're using a very, very, very large wingspan. It's about 6 feet long in wingspan for a little cube the size of a cell phone, basically. That's all it flies, because you need to move a lot of wind, right? A lot of air to lift. And also, we cannot move too much mass yet, because we didn't know if it would be able to fly anyway. So now that we know how fast we have to spin, we know how light we can build things now. We're hoping that the next wave of missions to Mars can fly helicopters that actually have substantial payload, as in bigger cameras and scientific instruments, but also small sampling tools like nanocores or mini cores that you can actually drill a little bit, much like you do in your wall, right, with your Hilti, and just get a little core and bring it back to the lander. So that'll happen, but that might take 15, 20 years to get there. But yeah, we're going that. And part of the reason of that, I think this is where you're going with the question, is that it's much faster to fly than it is to drive. It's about 100 times faster, if not more. So we're working hard for that. And if you're curious about future flying missions, there is one mission called Dragonfly that NASA will launch probably in 2026, if everything goes right, to Titan. And Titan is a moon of Saturn that has an atmosphere that is thicker than an Earth. So it's about 1.5 times Earth. So it's very easy to fly. So NASA is flying a drone with 6 rotors, like a hexacopter, the size of a small car, of a mini car. Because on Titan you can fly for cheap, right? Because you have a lot of air to lift. So that's kind of the compromise here on Mars. Yeah.
One more question. Was the number 26 came out because of the weight, or why did you choose 26 samples?
Yeah, it's a mass consideration. Yeah.
Okay. Thank you. Thank you so much. I really appreciate that. I think our audience were delighted, and I'm very sure that this recording will be watched again and again. We appreciate it.
No, thank you for having me. It's been a pleasure, and I wish you a happy ending of the family day.
Oh, thank you.
To be with you, and yeah, see you.
How's the weather in St. Louis right now?
Oh, pretty nice tonight. The fall is coming in here, so about 70 degrees, and it's dark, as you can see now.
Well,
yeah.
My son was stationed in St. Louis for a while. He just wrote me in the chat that when you were talking about the Mars weather, he said it's kind of like St. Louis.
Yeah, it can get pretty miserable in both ends, and summer and winter. But so that's why St. Louis is a big household name in Mars, because we know tough weather. So
thank you so much. We appreciate it.
Thank you, guys.
Take care. Thank you, Jessica. I'll send it to you.
Okay, great. Thank you. Let me just All right, thank you everyone for joining us for our keynote. That's always one of the most exciting parts of our Family Science Day. Right now, we're going to take a quick break. We're going to leave the webinar on. So all you have to do is join us at 7 p.m. and we're going to start right back up with our schedule with What's in the Sky Tonight, which will be presented by Justin. And during this time, we do encourage you to check out our video library, some of our new and past recordings from our last Family Science Day. So I'll drop the link in the chat, but it's the same link you used to get here, collegeofsanmateo.edu/family science day. So then we'll see you at 7. And oh, thanks, Mike just put that in the chat for us. So we hope to see you at 7 o'clock. Thank you guys.
Thank you, Jessica.